It's the same younger than our further Yes. That one is
Muy buenos días a todos. Good morning. It's really for me a pleasure and really delighted to introduce you today Professor Bruce Balick. Professor Bruce Balick got his PhD in Cornell University in 1971. And then he was a student at the NRIO at Charlottesville. He remained there until 1973 when he moved to Lick Observatory, and in 1975 he moved to Seattle University, where he's been all these years. He's really one of the person I can say that is really making, he's made a major contribution to the field of planetary nebulae. I still remember his 1987 paper where he introduced the generalized interacting stellar wind model, so that finally we could understand why stars were able to produce bipolar planetary nebula. That was a major achievement. But he didn't stop there. He kept on producing papers, and he's very, he's touching. At any meeting I've met him, introducing new students. If you ever had the chance to stay in the field, that's because Bruce Balick at some moment got near to you, and you feel really a friend and some people to trust. Now he's here visiting us for a few days. He's going to be talking about pre-planetary nebula and how they are shaped. He's been working for a long time on hydrodynamical models of planetary nebula, and now he's looking at the very details of the very origin of the shaping of planetary nebula. He's also working very actively on planetary nebulae in M31, where he's been working, not collaborating, but by the side of my postdoc, Xuan Fang, and they are making a really impressive work on this. Now we are going to start a collaboration. This is the very first time we collaborate, but we are so glad to start working with each other that I think that's going to be a lot of fun. So I'm not going to spend more time, just introduce you to Bruce Balick. Thank you.
Martin, this is our first collaboration, and it's sort of like getting engaged, isn't it? We're going to really find out how well we like each other.
Yeah.
It's my pleasure to be here. It's my pleasure to give this talk, and I'm going to start slowly, but then I'm going to accelerate. Let me point out my collaborators, and in particular Adam Frank, who was my PhD student. And in a grand irony of cosmology, I am now his student, right? So I taught, he studied under me. He's always been a theoretician working on hydrodynamics. I had no idea what he was doing. He was a great student. You just let him go, and great things happen. Over the years, we continued to collaborate. And in 2011, when I retired after just clogging the HST, the Hubble Space Telescope archives with images of planetary nebulae, costing the US taxpayers anyway, I must have cost them well over $2 or $3 million, right? And in retirement, I thought, well, you know what? Maybe I ought to try to understand what I did. And so I haven't been in the field of hydrodynamics very long. I entered in 2011, became Adam's official student at that point, and I've been learning it ever since. It's fascinating. It's just wonderful. All these ideas that I had about the way planetary nebulae evolve, what drives them, how their shape evolves. Every idea I ever had is wrong. And it's fun to learn that. I mean, unfortunately, at the end of my career, not the beginning. Now, one annoying thing about many talks, and this will be one of them, is that the speaker gets up in front of you and says, everything you know is wrong. I'm going to tell you what's right. This talk is kind of like that. Right? So, and I'll try to be careful to explain not so much the history of the field, not dwell on the misconceptions that I think are endemic among people who work in this field, but rather talk about the insights that I've learned in the last 4 years. So that's the focus of the talk. The goal in running models, as you know very well, is to go back in history. So you take what you know about the universe today, observations, and from those and a model, the physical model, you try to unwind time and go back to the beginning to see what happens. Now, my goal here is not, I wish it were, but my goal here is not to determine how mass is ejected and shapes the planetary nebula. Starting from the present time and using physics to work backwards, you can't quite get all the way back there. It's like the Big Bang Theory. You know, you can get to the Planck time, full stop, no more physics, right? And that's a problem here. But Adam and his group are working on mass ejection mechanisms down on scales of 10 AU and creating outflows on the scales of maybe 100 AU. My smallest pixel is 500 AU. So this summer I'm going to go to Rochester and work with Adam, and we're going to try to build an interface from the models that he and his students are calculating into this model, so that we can take the models of the mass ejection, which lasts maybe a few hundred, well, it lasts a long time, but the size scales are just so small, right? HST couldn't come close to resolving them. And so we have to build an interface from the little size scales in which he works to the much larger size scales that match current observations. So just be warned, I'm not going to tell you how it all happens, but I'll take you back to within a few hundred years of the beginning, and it gets pretty interesting. I don't have a clicker, but I do have a... Hang on, okay. So for people in the audience who never had Astronomy 101, that's not you guys. Here is the HR diagram, zero-age main sequence. You know this track, and I'm not going to dwell on how stars evolved from the red giant branch. Planetaries, their history really is built here. The central star climbs the asymptotic giant branch on time scales of about 1,000 years, and then takes off to the left, evolving very rapidly to warmer temperatures, but without changing the luminosity. What happens in the star occurs so fast that the luminosity can't keep up with it. But that doesn't last forever. And after a few more thousand years, the star ends up out here, way off to the left at 100,000 degrees, right, and starts its descent down to the white dwarf phase. Now, planetary nebulae, the ones that are ionized, tell you about, or are current with this track up here. That is, the gas that forms them had already been ejected along this part of the track, And the planetary nebulae that we see are the result, are an outcome. And it's very difficult to trace their history back here for one simple reason. When the surface of the star exceeds about 30,000 degrees in temperature, the gas is flash ionized. And the gas that had been ejected over here at temperatures of 10, 30 degrees Kelvin suddenly finds itself at 10 to the 4th degrees Kelvin. And so its thermal expansion is like a tsunami that just tears through all the older gas that had been there before, messes it all up, and it's for that reason you can't go backwards from way over here. The data that I will be showing you, most of it is in this region of the HR diagram. So the planetaries that aren't yet ionized are known as pre-planetary nebulae. And if you want to study how they formed and how the gas was ejected, you want to be over here, not there. Right, that didn't stop us from studying planetary nebulae for centuries. But the main reason we studied planetary nebulae for centuries is just they were easy to see. They had bright emission lines. You could take good photographs of them. Even, you know, Herschel could do it. Those days are, I think, are over. The gold that you're going to mine has to be done over here. Now, the problem, of course, is when a star is here, it's not ionizing anything. In fact, for a while, it's hiding inside the dust that forms in its atmosphere, and it's not until that dust begins to go away that optically, and also in the infrared, you get a view in. But it's, that sounds terrible. Hubble images are images obtained in scattered starlight. The star is cool, but really luminous, right? 3 times 10 to the 3 solar luminosities. It's just emitting zillions of photons in the near infrared and the far red. That lights up the dust, and so we can tell from images where the dust is. We can tell where the dust that can see the star is. There may be more dust that can't see the star, and we're not going to see that dust optically. So we go to ALMA, and we look for signs of molecules in carbon monoxide in the region around the star, and that's a burgeoning field, thanks to people like Martine and many other people. ALMA's just going to ALMA will revolutionize what we know, and everything I tell you will probably turn out to be only half right, but that's okay. Now, when the star climbs the asymptotic giant branch, it undergoes thermal pulses on timescales of 10 to the 5th years. Even the most massive stars that climb this, and that's under 8 solar masses, can't generate thermal pulses much more frequently than that. So a planetary nebula is typically, we think, formed right about here in the final, not that one, the final thermal pulse, of which there are dozens. And it's then, the pulses increase in luminosity, and it's then when luminosity-driven winds really do their thing. By that time, the outer layers of the star are at the Earth, or all the way out to Jupiter. They're barely gravitationally attached to the star. A thermal pulse can come along and create light, which just takes the outer layers and pushes them out. Now, if it were only that simple, because stars are round, radiation comes out of them isotropically, and so we should be forming bubbles, and that's not what we see. There are Hubble images of 50 or so pre-planetary nebulae, and not one of them is round. Most of them are either bipolar, they have a lobe going this way and a lobe going that way, or they're kind of messy. None of them do what the textbooks say they should do. So there's an interesting story here. And that brings us to why we work in this field. That is, we don't understand what happens at the end. It's that simple. Stellar evolution at the end doesn't, it doesn't play by the same rules in the post-AGB evolutionary phase as it did before then. Something changes. And there are all kinds of ideas. For example, All kinds of ideas why that happens. One of them, the most popular at the moment, is that there's a close binary system, and the tidal interaction of a compact star with its bloated companion forms mass loss, which is sculptured, which is structured. So you think about that for a second, yeah, that ought to produce a flat plane of outgoing material, and which doesn't have Keplerian motions. Too bad, because the ALMA observations, when you study the disks, and there are some, do have Keplerian motions, which is suggested that those disks came from the outside, right? Not from the star itself. Another idea for shaping planetary nebulae is that magnetic fields anchored to the white dwarf forming in the core down at the center of this AGB star are somehow impregnating the outer layers of the star, and so when they come off, carrying the magnetic field with them, there's a structured flow. And you think about that for a little while, and you realize, you know, the things that magnetic fields love to make are thin little jets, not lobes and things like that. So we're still looking for paradigms that actually work. We're making some progress, but because the size scales are so small and the observational constraints are so puny, there's a lot of field, a lot of parameter space to explore, and we're doing it. And Adam in particular and other groups around the world, Lawrence Sabin, sorry, that's not right. I can't remember her name right now. There's some marvelous work being done. All right. We're not going to talk about that much. We're going to talk, my talk is based on observations. That's my foundation. I'm an observer after all. And we'll move from there into the modeling that I've done on those observations, hoping to provide good hard constraints on these models of outflows at a time of about 100 years after the outflows begin. We're going to work our way back and look at what the geometry of the outflow may well have been a long time ago, and that will be very helpful to them. Now, planetaries aren't round. They have all kinds of shapes, and many, you've seen pictures like this before, and you look at these things. How many of you have used Hubble for imaging? Nobody. Oh, you have, of course. So, but you can imagine the process. You write this incredibly complicated proposal, you submit it. Only 1 out of 6 or 8 proposals is ever awarded time. And if you get some time, you say, God, it's a downhill ride from here. At some time, and you don't know when that will be, when it's convenient for Hubble, your targets will be observed, and you'll know that only because you get an email saying, bing, your data are now in the archives. So you don't know when the observations are going to occur. I mean, you can kind of find out. So this email arrives, and with you know, a little bit of nervousness and apprehension, you go to the archives and you grab the image, and they look like this, and you say, God, this is spectacular. Everybody says that. But the elation lasts about 5 seconds when you realize you got the time not to take the pictures, but to explain them. That's when the cold sweat breaks out. How in the hell are you going to do that? So this talk is a step in that direction, and it's in the center of my research for the last 4 or 5 years. But the shapes are absolutely fantastic. There's a lot to be learned from these things. The ones you're looking at here are all ionized, and they have famous names. So did the ones before. Well, sorry, let me go back. This is a pre-planetary nebula. There's not an emission line coming out of that thing other than molecular hydrogen and carbon monoxide. So radio molecules, almost all of which arise in here, in that where we can't see anything because of the extinction. And that's what we call a disk, but it isn't, because when you use radio interferometers to map the CO down there, it's coming out in jets, all lying in the same plane but going in different directions. That's not a disk. That's some sort of an outflow disk. I said just a moment, I'm just contradicted what I said just a moment ago. The disk, I said, doesn't come from the star because its motions are Keplerian, but not in this case. This is an exception. There are all these rings out here that carry a historical story of the way in which the star behaved before all this inner stuff, moving at relatively high speeds, that it has a short dynamical lifetime. This is a history of an HEB star a long time ago. And we're spending a lot of time during my visit here talking about what might have happened, looking at the rings, trying to measure the speed at which they flow outward, because that'll tell us how old they are, if their motions have been more or less constant. And that's not what I'm going to talk about today. It's a great subject, though. And there are rings here. I mean, rings are not uncommon, but we haven't decoded the message yet that they're trying to send to us. And they're always round. I mean, really round, or they're round segments. And you know, I said before, this round star doesn't produce round outflows. Wrong. It produces round rings or round segments of rings. You see the same thing in these objects. These are all ionized. The shapes are marvelous. They're really cool. But anybody know what they mean? Roughly 10% of ionized planetary nebulae are these bipolars, two lobes in opposite directions. That fraction goes up to about 50% when you look at pre-planetary nebulae. So this kind of a geometry is relatively common, at least at first, and I think the tsunami of ionization takes those objects that aren't really, really, really bipolar and messes them all up. So when the temperature rises to 10 to the 4th degrees, the sound speed rises to 10 kilometers a second and stuff starts moving every which way. But look at the beautiful shapes here. And again, I'm not going to tell you how this works because I don't know, but this is the big prize this is the pot of gold we're all chasing. I will, however, spend quite a bit of time on this one because it's so well studied, and a hydro model that I just published at the beginning of the year, doesn't it, if I don't say so myself, does an astoundingly good job at matching all the details. Here's some more of these things. We used to think that this was a more recent ejection than the bipolar that surrounds it, but when we stuck long slits down along the symmetry axis and in other directions, we learned that the kinematic age for everything you see here and that are identically the same. So either these things were born at the same, well, they were born at the same time. That's not to say there was some sort of an eruption, a sudden eruption, but the kinematics of all these features have the same dynamical age. And I'm going to come back and say a little bit more, because one of the things that is poorly or misconstrued, very frequently misconstrued, are the speed patterns that we see in these objects, at least according to my hydro models. So the big prize is to figure out where all this stuff comes from and how it comes from there, and to learn about stellar evolution right on the way up to the HEB when weird stuff starts to happen. Now here's a gallery of pre-planetary nebulae that I selected because they're not a mess. As I said, 50% of these things are just blobs with arms and legs and loops and this and that. Chances are, if you're doing hydro models, you're not going to understand those things in any detail, but you stand a chance here. So in this talk, we're going to spend some time on that one. M29, the bipolar I showed previously, is not in this gallery because it's partly ionized, but not by the star. It's ionized by shocks that are produced when the wind flowing outward slams into the medium around it. I'm now working on models of things that look like cylinders because I can't yet figure out how a point nozzle makes a tube from its outflows. I mean, I can get that to be a transient feature, but it's not a long-lived feature, and so that has, to me, has become a very interesting problem. If there's time, I'll touch on that at the very end. That's my work in progress at the moment. Now, I decided to start with the conclusions before you go to sleep, so that if you walk out of here, you might have learned something in the way of a take-home message. We're going to construct models of these things based on steady flows from the nucleus. I'm going to create, I think of a jet as a little thin thing. We're going to create sprays, like the stuff that comes out of a paint can, where the momentum flux is primarily along a symmetry axis, but there's stuff that comes out over some range of angles in addition to that. So these are all, my models are the results of steady sprays. And those sprays have the attribute that they're completely light. What do I mean by that? What I mean is, the spray can analogy breaks down here. In my models, the spray coming out of the nozzle has a density of 1/10 or much lower than the gas which is around it. So it's a light spray, a very light spray. Not even that. Right? Very low, high speed, so there's a fair amount of momentum flux in it, but the density is way, way low, and the first thing that happens as this gas comes out is it begins almost immediately to feel the inertial pressure of the gas in the ambient world, the outside world, which I assume to be an AGB wind. For model purposes, it's static. It's probably moving at 10 kilometers a second. That doesn't matter. So the outside world is this steady state wind with spherical symmetry, a density that declines as r to the minus 2. So the density is concentrated near the nozzle itself, and it turns out that that's when most of the shaping of the lobes takes place. So at the nozzle, there's a diverging spray. The outcome that you see in the pictures behind me here, the lobes go up and they close. And it's only with very light sprays that you can get lobes that close as the outflowing gas is trying to push its way through this AGB wind, which is much denser than it is. That's right down here. And what happens is that this light spray pushes that stuff out of the way as best it can. It's not very good at it. One thing that happens is that the speed of injection is typically much, 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 much higher than the speed we see for the gas that it displaces. Why is that? Well, it's a density thing. Once the spray has displaced roughly its own mass, the mass that it has displaced now is not moving as fast as the spray, in fact, begins to confine the spray. So when we look at these lobes here and we measure their expansion, we're not measuring the speed of injection, we're measuring the speed of displaced material, displaced by that injected gas, material that picked up its momentum from the injected gas, but is moving much more slowly than the injected material itself. That's a very common misconception. Why do we know that? I should go back one. Oops. With this exception, the lobes are all hollow. So whatever's blowing into them doesn't scatter as much starlight as the stuff around the outer edges. And we think the dust is well mixed. In fact, the origin of the dust is the star itself. Right? So if you see a hollow lobe, what's going through it has a lower density than the edges of the lobe. And that's why the models that I run are always light ones. And there are a lot of observers for a long time who look at the lobes, measure their Doppler shifts, measure the mass they see in the lobes and say, oh, that's all came out of the star. This is stuff which the flow from the star has pushed to the edges. And most of the mass that you see here is displaced AGB wind, not stuff coming out of the star. Not quite all of it, but most of it. And so the lobe edges are not material from the star. They're ambient material pushed around. the speed of outflow that you measure, I don't know, with a long slit or whatever you have, it may be ALMA, is not the speed of the injected gas, it's the speed of the displaced gas. And I'm going to stick my head in the mouth of a lion when I go up to Madrid on Friday and work with your absolutely fantastic ALMA observers and try to sell them what I just told you. And it's going to be we'll see if they take me out to lunch afterward. Are they listening in? Uh-oh. All right. In addition to all of this, there can be thin shell instabilities at the thin edges, especially at the leading edge, when the pressure of the gas upstream, that's this 1 over r squared AGB wind, drops to just about nothing, and the gas moving through it will break up into knots. We'll see some of that in the pictures, but it's not a big deal. Okay, so this is to remind you that when you look at the contrail of a jet, you're not seeing what came out of the jet, you're seeing condensation in the displaced air. It was compressed, cooled, and pushed to the side. Same thing here. So it was very hard from observations of the contrail to reverse engineer the jet itself. Are you with me? Am I? Okay, good. All right. Oops. So I put this slide in here because I give this talk to a wide variety of people. There are jets of all different geometries, cylindrical jets, Gaussian tapered sprays, that's the spray can, and that's what I'm using in the models. But I had to, this spray can has a uniform flow out through the nozzle. You can buy them any way you like them. But this illustrates a couple of things. First of all, if the gas comes out in a cone, then it's not going to interact with the gas, the AGB gas around it, because both of them fall off as 1 over r squared. The pressure will just carry that stuff onward, and what you get with a purely cylindrical flow, the lobes look like pizza wedges, sharp edges, around top. We never see that. They're ring-like sprays. In any event, you can, when you're doing the hydro models, you have to pick a paradigm, or maybe you'll pick 1 or 2 of them to try. And this one's mine, right here. This illustrates light and heavy flows. So this is a heavy flow. The density coming out of the nozzle is way bigger than that of the air. And the stuff coming through the nozzle says, I don't care if there's air there or not. In fact, I don't even feel any air. I'm going straight. So heavy flows reproduce their own ejection geometry, and what you get is a lobe that just grows linearly with time. It doesn't change its shape. And the shapes are not interesting. You don't get closed lobes, for example. So my flows are light. This is a leaf blower. You can't see the air, but you can see the leaves, right? And the geometry of the leaves is not necessarily the geometry of the air that blows into them. The air that blows into them is slowed down by the leaves. I mean, you get all this. And this slide here is meant to convince you that the flows are light, the lobes are hollow. We're not seeing light from the stuff moving through the lobes, at least the edges of the lobes dominate what we see, not the cores. So putting a long slit along here is going to tell you what how the edges move, not how the stuff moving through them moves, because it's not emitting. And I can't think of any tracer of high-speed flow, the 200-300 kilometers a second, that would be of any use. I wish I could think of some. You can get X-rays out of this stuff, but we don't have the technology to use the X-rays to investigate the properties of the flow itself. And basically speaking, the flow is just constant speed streamlines. So there's no real temperature associated with streamlines that are very well behaved. They're not interacting, they're not hot, they're not cold, they're they're A temperature. I mean, they're not thermally, there's no thermal pressure, a little bit. But eventually those flows reach the edges of the material that they have displaced, and they crash into it, and along that locus, the interface between the streamlines and the displaced gas, shocks arise, and they create emission, and we can look at them, and we do. I've said all that. There's another type of a flow called bullets, right? So these are bullets. These are much denser than their surroundings, and you spit them out, and they just keep going, leaving not a vacuum. Oh, come on, a stagnation pocket behind them, and the material that they displace on their way out follows them in a bow shock. We're not talking about, there are these two, and as far as I know, only these two examples of pre-planetary nebulae with bullets in them. And I'm trying to understand sort of the general properties of the stars. So we'll just consider these anomalies and go on from there. All right. Now we'll get anecdotal. We're going to talk about M29, or Minkowski's footprint, which he discovered in a long time ago, 1946? Yeah, I think so. So, you know, if you're a nebular observer, you know M1 this and M2 that. This is one of those. This one has a particularly wonderful symmetry, and when you look at it with HST, like this, you see an incredible amount of detail. So I'm going to boast a little bit. I was the first one to observe this, and when the pictures came down, I was so ecstatic, and I sent them right back to the Institute and said, we have to do a press release on this. And then, you know, a moment later you realize, what did I just do? I don't know how this works. What are we going to talk about in a press release? Anyway, that's what we're going to talk about, and we're going to build it all. In fact, there are parts of M29 that you don't see here, but which you do see in long exposure images. So this is, of course, the central region of that. There's another pair of blobs out in here. There's a faint connection back to the... what people always used to say, and I'm going to use the word wrongly, as I hope to convince you, is that these are older ejecta. There was a previous episode of ejection, and the last episode of ejection produced these knots here and influenced the medium around them. Right? So these knots are driving through something. Here's that putative bow shock. I mean, it's just not going to work, but it's easy to think about that. Right? We love Walt Disney cartoons. We love to abstract and simplify, and I've done this myself. The problem is, well, one of many problems is when you measure the Doppler shift of this and that, this one is older than that one. So there's something wrong with that picture. And in the hydro model unifies with almost perfect success all of these things. It explains why there are nested lobes here. It explains why there's this thing that looks a bit like a bulb with a knot up near the front end of it. It explains why the edges of the inner bulb, seen here, these are infrared images. Blue is iron 2. Iron 2 is formed in supernovae. You've really got to slam the gas at 100 kilometers per second or more in order to excite iron 2. And you see it here, but you don't see it out there. The orange is molecular hydrogen, which is shocked far more gently. So there are shocks here and there. There's almost certainly a contact discontinuity in between them. If you are into the hydro, I'm going to skip that. And then there's the stuff up here. The model has to connect all of those dots, and it will. Oops. So the knots have names, as you can see here. obviously the spatial scale of the optical image and this Gemini infrared image are the same. The bulb is shocked in iron 2, and the streamlines are just slamming right into it, almost certainly. The outer sheath here is separated from the bulb. There's a shock there in molecular hydrogen, much gentler, much slower. There are these feathers that extend past the edge of the bulb, and they have the same ionization and roughly the same kinematic properties as the gas down in here. So they almost look like extensions, except they get this kind of feathery shape to them, which is significant, or will be. All right, so the outer, we know from optical observations that in the optical, the outer sheath is all reflected starlight. The star has a very unusual spectrum, and the light that comes from these things also has all those characteristics in it. But the bulb is emission lines, all of which is modeled extremely well by shocks on the order of a few hundred kilometers a second. So that's giving you a clue to the speed of the streamlines which are shocking the gas, a couple of hundred kilometers a second. Repeated Hubble images of these things show proper motions, and this thing's close to the plane of the sky, show unmeasurable proper motions over about 15 years. Right, these things are kind of stalled. In the hydro models, their speeds are 30 kilometers a second, which is below the threshold for detecting proper motions with the HST images to date. I'm going to skip that. So here, let me go back to this. One thing I won't say later, so I'm going to say it now. These things don't emit their own emission lines. Rather, they scatter starlight. And I said the starlight has this incredibly characteristic, almost unique spectrum. It's a spectrum of a symbiotic star. And we see that stuff coming from here and here. So we can measure from the scattered light, we can measure the Doppler speed of these things, taking into account the speed of the gas emitting the lines that they reflect and taking into account their own motions in space. This is not difficult, and it was done by Romano Corradi. Well, actually, it was done in the 1990s by, I think it was his thesis advisor. These things have speeds, outflow speeds, close to 150 kilometers a second with some degree of uncertainty. But they're certainly a lot faster, moving much more quickly than the knots inside. All right, so how are we going to, oh, I skipped a slide. Let me go back. Here are the kinematic observations. This is an optical long slit spectrograph, spectrum. There are little knots in here that correspond to these knots right in there. They're not a part of the story. They're not global in nature, and they do really weird things. If there's time at the end, I'll show you. I mean, it's incredibly weird. But we're going to ignore that. The iron 2 lines arising here have knots. So the spectrum shows the 2 knots at the end here, N3 and S3. But generally speaking, there's a linear change of the average speed with distance from the center, which is very characteristic of preplanetary nebulae and planetary nebulae as well. The slit passes through this region. Of course, the slit is placed here, and we see 2 parallel lines, presumably each one of them coming from opposite sides of the outer lobe along the line of sight. So they're moving, it looks like, transversely at speeds of about plus or minus 15 kilometers a second. So the outer lobes are moving sideways. The bulbs contain light in which the Doppler shifts increase with distance from the center. And the model has to account for all of that. So this is a really tightly constrained model. The observations, at least in my experience, there's no wiggle room. When you hit the right answer, you know it. Or, sorry, I should never say the right answer, the best answer, but you know it. Okay. So what's the paradigm we're going to, I mean, I already told you I use sprays, but in a general talk, it's useful to go over the other kinds of paradigms that compete with it. So this is an outflow paradigm, right? The knots pop out along with high pressure gas from inside some bottle. That doesn't work very well. Well, maybe it does, but these things are, the analogs of these are N3 and S3, and they're just kind of sitting there. So wrong paradigm. There are plenty of others. There are steady flows that come from nozzles, right? And these flows, well, there are those kinds of flows. There are isotropic flows, which are constrained by some equatorial thing, which is an inertial constrainer. Magnetic bombs, so magnetic fields come up out of the star, and they come out with a preferred axis. Magnetic fields have an energy density that drops off as 1 over r cubed, so they're quite effective near the surface of the star, but after that, it's easy to overwhelm them with thermal effects. But still, it's a paradigm to be considered. These things tend to want to make jets that work their way upward, right? And the fields then sweep back behind it in the gas, basically in the bow shock from the head. So these fields here are not dynamically important, and the field in the star produces a jet, which we don't see. All right, so here are the results of my simulations that extend over the dynamical age, which is supposed to be up here somewhere, 2,500 years. So the form of this, there's a spray coming out here. Where's the density? The density's hiding. I apologize. The density distribution is hiding behind this thing here. Let me see if I can make it go away. There we go. So the densities are coded 2 different ways. I use color because you need color to help with the dynamic range. But if you're not too interested in all the details, the grayscale is perfectly good. The streamlines are in here, right? And they're just freely flowing. They don't yet know there's a universe that they're going to run into. The material around the edge is displaced material that used to be around here, but got pushed out of the way by the growth of the lobe. Now, one thing that I want to draw your attention to is that little diagonal line. This is the temperature distribution. Sorry, this is the speed distribution. Can I stop this thing? Yeah, I can. Can I do it advance? No. All right, next picture. Here's the density distribution, again, as a grayscale and a color image. This is the speed distribution at the end of the simulation. And notice red is the outflow speed that I assigned, 200 kilometers a second. And there's this thing right here where the speeds drop to just about nothing right away. So this is called a reflection shock, and there's a real shock there, which in my models accounts for the shock iron 2 around the edges of the bulb. And the streamlines pass through this. They're not especially slowed down. Their speed stays high. But what happens is that their kinetic energy is converted into heat, which shows up over here in the temperature plot. So up in here, this stuff is moving outward, but it's very hot. This stuff is just streamlines freely slowing. So there's that important change in the character of the gas. The stuff coming up here is trying to swim its way through the outer part of the AGB envelope. It's deflected by that envelope, and it wants to try to reconverge to make these knots up here at the top. In the simulations, I wish I could make better knots, and I can't, but they're kind of there. And they have speeds, given right up here, of around 150 kilometers a second, which is exactly what we measure from the proper motion studies of the Doppler shifts of the light reflected from the dust that they have in them. This thing down here is a knot, but it's just creeping along. So the hydro models, there are many more details here, I don't want to go into them. The hydro models are getting the basic observations largely right. And M29 is fairly complicated, and we're getting pretty close to getting the details, accounting for the details. This shows the first few hundred years of evolution. I've just over-plotted the models one on the other, and what we see is the rapid evolution of knot N3. So the gas comes out of the nozzle, which has a spherical tip on it, because it's a spherical diverging outflow. And this is gas from the AGB wind, which is being pushed and compressed and shocked. And the gas in these things tends to creep up along the edges and pile up into a knot. So that's the origin of N3. They weren't ejected down from the nozzle. They formed early on in the flow. So this is what I present to the people who are doing the hydro models of what happens down deep inside, way down deep inside that circle. All right. What was that one? Oh, so this shows you the streamlines as vectors. And notice in the outer sheath, which is hot, I don't have the temperature image here, this is just expanding into the AGB wind laterally, accounting for the shocked H2 along the edge, which is moving outwards in the X direction more than the Y. So, you know, a lot of the details are done here. Okay, I'm going to skip that. Oh, wrong. We already saw that. I'm going the wrong way. Sorry, I'm used to a little clicker and I don't have it. So that summarizes what we learned. Here's another case. This is the Calabash Nebula. This is reflected starlight, the yellow, and the blue is shocked H-alpha emission. So there's something apparently coming up along the symmetry axis from the center, and somehow or another, hot gas is being generated either down here and ejected outward, or somehow in the interaction between this and whatever. In the hydro models, this doesn't interact with much of anything except right there. The collimation doesn't disintegrate as this spray diverges and propagates outward. These are more observations. This is the molecular contribution. The CO, the gray is the optical image. The CO all lies right there along the very spine through the center of this. This is 12 CO and this is 13 CO, right? Or the other way around, I can't see from here. Oh no, this is CO 0 to 1 and 1 to, I can't see. Two different CO lines, but both of them are 12 CO. This is the Doppler shift of the CO measured along the spine, and it's got this form here which is absolutely simple. So for many years, those of us in the field mistakenly said, Hubble flow. Right? There was an explosion down here and stuff just shot out and the faster stuff got the furthest. No. If you want to match all of this, you need steady flows that interact with the medium around them, and you'll see the hydro model in, but I'm out of time almost. I'm going to move on. So this time, the quark paradigm works pretty well. You launch, why do I keep going in the wrong direction? No, sorry, okay. So I launch a clump, a bullet, which disintegrates by now, after 1,100 years, shocks reverberating through this thing as it moves outward are beginning to tear it to pieces. That's more true for the knot at the end of the big lobe than it is for the knot at the end of the small lobe. Both knots are ejected at precisely the same speed. All that's different is the density of the ambient medium on one side and the other, which I won't even try to explain to you. At the same time, the spray comes out here and forms the bulb. So the streamlines are doing what they did in M29. They're going out here. The opening angle is a little bit wider. So this is a composite model of a knot which flows through a lobe, and the knot disintegrates about now. And I must have run 100, if not even 200 models. They're pretty fast if you do them in 2 dimensions, looking for the sweet spot, and this is the only one I ever found. Launch the clump first, launch the spray first, change the speeds, mess with the densities on the outside. I've done it all. So here are the properties that I assigned to the flow at the base of the bulb down here. And the spray is 225 kilometers a second. Oh yeah, different speeds. I said different densities. I'm wrong. The densities are the same. Anyway, these are the parameters. The densities and the speeds here yield outcomes which are a very nice match to the observations. All right. So this is a parameter study. I twiddle the ratio of densities of the flow on the outside and the AGB wind around it at the nozzle, and you get pretty much the same outcome with more thin shell instabilities in one case than in the other. So this is what I'm working on now. There isn't time to go into the details. I don't have a whole lot to report. I have tried every paradigm I can think of of flow into AGB winds. Here are the data. This is what the thing looks like. It looks like a cylinder. Notice that it gets kind of ragged out in here, which seems to suggest that hydrodynamically there's a thin shell or something which is creating instabilities when you get out far enough. This is a long slit spectrum of the molecular hydrogen. It's just like the one in M29. Very, very nice slope to it. Brighter. This slit goes right through the symmetry axis. So this thing here is a sheath expanding laterally. And what's weird about it is that its geometry is cylindrical. And the simple paradigms, so just launching stuff with different paradigms into an AGB wind, produces all sorts of wonderful results, none of which are very convincing for one reason or another, and there isn't time to go into that here. If you're interested, I'd be happy to talk to you afterward. Wrong button again. So this is a bullet model. The bullet comes up and immediately begins to disintegrate because of the shocks reverberating around through it, and it's torn apart and pretty much shredded after 1100 years, which is the age of this. Here I launched just plain old cylinders of stuff with parallel streamlines. The base of the flow is what you see here, 7,000 AU. There's nothing in the image of this object which justifies a cylindrical flow. Just nothing, but you run the models to see what you're going to get, and you get what you think you're going to get. Cylindrical models give you cylinders. In some cases, the flow is light enough and instabilities set in after a while up here near the outer edge. This is probably the best match to the data that I have. This one isn't bad. The others, this one isn't hollow. Here the density inside the flow is way bigger than that of the AGB wind around the outside, and we're looking at a hollow lobe. This one isn't hollow, that one isn't hollow, and that one isn't hollow either. This is the only hollow one. In order to match anything at all, I have to launch the flow at 625 kilometers a second. The Doppler shifts, after correction for inclination, tell you that the actual outflow speed at the end is 135 kilometers a second. So the injected gas is moving 5 times faster in that model than is the gas that we observe. And then here are the spray models. And you do okay, but what you notice in the time evolution of these things is that the parallel walls don't stay parallel for very long. So you can force them to be parallel at 1100 years by picking initial conditions carefully, but the results, the outcomes are not robust. I mean, the initial conditions are not robust. So now, just in the last month or so, I started building disks in here for the flow to deflect off of to see if I could do any better. And here's the best I've done so far. The bigger picture shows the flow at 1100 years. I put the slide in just this morning, so sorry, it's not all that well annotated. This is the flow at half that age. And the walls are kind of cylindrical, and the disk helps a little bit. And I'm gonna play with other disks. This disk is concocted by theoreticians who idealize the world a little bit too far. So these are schematics of real live disks of CO seen at ALMA. And I'm going to use some analytical representation of them and just see if that helps. So in short, that's the talk. You've seen this gallery once before. You've seen these conclusions all before. Right? And the purpose of putting this talk, I mean, this slide back at the end is if there were time, we'd quickly go back and talk about the conclusions and see if they still make sense to you. They probably didn't make sense at the beginning of the talk. Maybe now they make sense. And if you're a small handful, there are a few of you, maybe, there's one right there, who care how or why the outflow speed pattern rises linearly with distance. So there has to be a robust explanation for that because you see it over and over and over again. These are all speed versus distance diagrams. For those of you who care about that, I'm just going to put this up there. It turns out that this is a robust result of the models that I've run. Not all of them, but most of them. And the increase of speed with distance has nothing to do with ballistic ejection from a brief event. Absolutely nothing. Although it turns out the slope of the relationship, which is the age, right? It's the Hubble age of the flow, that works pretty well to give you the actual age of the outflow. But there are two major reasons why the speed increases linearly. No. Ask me later if you're interested. I'd like to leave a little time for questions. Sorry. Who objects to that? Nobody. That's the talk. Thank you very much.
Great talk. Do we have any question? Oh, Jesus.
So you said that this is what I worry about. Good.
So you said that we don't have to notice these X-rays from protoplanetary nebulae, but we actually have one protoplanetary nebula that we actually see the X-ray emission. And from your models, I can see that you can predict a point source near the clump. And this is actually what we see in Henai's 3.
So if I understand you correctly, you're saying that models tend to predict knots up at the ends of the tips, the closed tips.
Have you estimated
Well, I mean, I get the knots at the closed tips because I set up the initial conditions. There are lots of knobs to turn. It's not hard to have open lobes. If you put a little more momentum flux in the flow at the bottom, it'll blast its way through the AGB wind, never completely convergent. So the fact that there are the lobes closed turns out to be a very tight constraint on how you set the initial conditions. Very tight.
But the point is that you will never see extended diffuse acceleration as in planetary nebulae, for example. So you will see like point, like very well determined. So we can see that now.
All right, we'll talk about it later. Let's move on quickly.
You assume that you have a low density outflow move. No? Okay. So you assume that you have a low density outflow moving within a much higher density medium, right?
All right. There's a way to solve that problem.
I try to speak louder.
You can do that, and I can hear better.
Okay. So in your model, you assume that you have a low density outflow moving in a much higher density
That's right.
medium. So, and your density, the density you assume in your models was something like 10 to the 4.
In order to match the brightness, the observed brightness, surface brightness, I have to have densities of around 10 to the 4th. In addition, we know something about the mass in the displaced gas from radio observations of molecules, and I have to match that mass, and that also takes a density of around 10 to the 4th.
But shouldn't that identity envelope show up in the ALMA observations? But I don't remember seeing that dense envelope.
I didn't show you any
but
it does.
But what I remember is mostly toroidal structures, not toroidal structures, tori, but not extended, circular or something.
Not sure I understood the question. Do you have a particular object in mind? Because ALMA observations so far are pretty few and far between. And I, at least, have been reluctant to draw general conclusions yet. I mean, I can say they ought to see the edges of lobes. They ought to see molecules that are excited by the shocks that form along those edges. The speed that they measure along the edges should be a small fraction of the outflow. And the only... What ALMA images have you seen of these things? There's the really cold one. OH231 is about to come out, and I'll see the image when I go up to Madrid on Friday. What else is there? ALMA observations of preplanetary nebulae. Yeah. So there's the Boomerang Nebula, and there the gases along the edge.
One is a water fountain by Sahai. I don't remember the name. IRA 1613 something. But what I'm saying is that an envelope of 10 to the 4 should show up with in CO. Yeah, I think so.
Well, the people who write the papers put that number in it. I didn't make that one up. And I think they get it by the CO is fairly strong, but they also look at HCO plus. And there are regions where HCO plus comes from 10 to the 6th. And so the CO that they observe tends to be often in a region where there's a transition from CO to HCO plus. But they also do what I do. They just say, well, the total mass has got to be the mass that an AGB star ejects. You make up a reasonable number, 1/10 of a solar mass up to the half a solar mass. And then I think they reverse engineer the density until they get that. But I could be wrong. I could be, because the CO lines don't have density diagnostic in them, right?
Depending on what line they have a different critical density. So if
So with ALMA, we'll get 6 or 7 CO lines spread across the spectrum, and then the temperature can be deduced. The density can be deduced directly. I think.
But there are shells that are, like ALMA has detected like shells around 8 GeV stars.
around 8 GeV, yes, but not in bipolar post-GeV stars. I haven't seen them.
But yeah, I guess the picture is that you have something roundish, and then it becomes bipolar.
I came here to learn. Let's talk after lunch. And I mean, there are a lot of people here who want to get out.
Any other question? I have something very particular. You claim that the central star of M2-9 has a peculiar spectrum. What do you mean by peculiar?
Sorry, which spectrum?
The central star, yeah, the optical.
The optical spectrum is entirely collisionally excited lines. There's not a trace of photoionization. Well, I'm lying slightly. There's the star emits a very broad symbiotic-like H-alpha emission line, and you see that reflecting off of dust everywhere. And in fact, the dust that it reflects from has its own motions, and you can trace that too. But there's nothing all that exciting about it.
Okay, but could you say that this is a symbiotic star?
Hmm?
Could you say that this is a symbiotic star?
I could say it's a symbiotic star. I mean, it looks like a symbiotic. It quacks like a symbiotic. It probably is.
Okay.
Yeah.
So that's that case a binary. Okay. So any more questions? Let's thanks again Bruce for his talk.